So, as I just mentioned, the use of this freezing is some technique is something very tricky, and one should be able to design the system in such a way that you have a proper combination of primary cooling and secondary cooling systems, and also see that the circulation of coolant is proper, and also that the frozen barrier, this so called frozen earth barrier is something that is maintained till it is required. Say for example, you need it for a month, it exists there and also works in a proper way, and you have to maintain that, and then all the design is based on the thermal properties of the soils and also the related response to freezing system. This is very important. This is a simple example, like the formation of a frozen earth barrier develops at different rates depending on the thermal and hydraulic properties of each stratum. Like you have, say for example, bedrock, you have a quartz gravel, you have a clay, you have fine sand. So, you have the barrier here that is developed next to the pipe or a shaft or whatever system. So, this is very important, it should be maintained. When a soft clay is cooled to the freezing point, some portion of its pore water begins to freeze and clay begins to stiffen. Why it works is that, say soft soil has lot of water content and the pore water freezes and clay begins to stiffen. So, if the temperature is further reduced, more of the pore water freezes and the strength of the clay markedly increases. This is actually the mechanism. And when designing frozen earth structures, it may be necessary to provide substantially lower temperatures to achieve the required strength. The thing is that we know that with reduce the lower the temperature, the strength is the it is going to be more stiffening, and the one should be really careful, because the temperature gradients should have properly understood. Like if there is you should have an adequate margin of safety to see that you get the required strengths. And then a temperature of plus 20 Fahrenheit may be adequate in sands, whereas the temperatures as low as minus 20 Fahrenheit may be required in soft clays. The frozen earth must first forms the shape of a vertical cylinder surrounding the freeze pipes. As cylinders gradually enlarge, they intersect, forming a continuous wall, like it is like this. Pipes prior to freezing, you have all these, that zone is getting developed, and then initiation of the freeze. Once it forms like this, then you can see that completely it forms like this. So, complete frozen earth wall is formed. So, you can see that at the top these are the bulbs or whatever is that frozen material, which is quite useful. If the heat extraction is continued at a high rate, the thickness of the frozen wall will expand with time. So, for example, you are trying to remove the heat from the system, that heat you are trying to recover actually. So, the thickness of the frozen wall will expand with time. Higher is the rate, higher is the expansion of the wall. Once the wall has achieved its design thickness, the frozen plant is operated at a reduced rate to remove the heat flowing towards the wall to maintain the condition. Once you get the thickness, which is quite sufficient to see that the design is satisfactory, the plant is operated at a reduced rate to remove the heat flowing toward the wall to maintain the condition. So, like as I just mentioned, like similar to a fridge, once you it has actual temperatures that you had wanted, but then subsequently you need only the power to see that the temperature is maintained, the same temperature is maintained. So, as I just mentioned, the most common freezing method is by circulating a brine, a strong saline solution like a calcium chloride. Okay. A chilled brine is pumped down a drop tube like this, a brine supply, and then you have the liquid here which is there. So, this area has that that creates that particular freezing. So, because of this process it draws the heat from the soil This is some sort of refrigeration unit. Liquid nitrogen process has been applied successfully to ground freezing in some places, and the cost per unit of the heat extracted is much higher than with circulated brine. The brine solution is somewhat cheaper compared to liquid nitrogen. Nevertheless, for small short term projects, particularly in emergencies, the method can be occasionally competitive. Because of the extremely low temperature, freezing with LN2 is rapid and high strengths of frozen clay can be achieved. This technology finds application in the following construction projects: underpinning, like keeping that in a stable condition, tunnel roof freezing, freezing of the cross cuts in tunnel tubes, clearing out of the tunnel fall-ins, forcing of the framework constructions into railway embankment, foundation skirting, removal of intact soil samples. Even to remove the intact samples also, like you freeze that area to take the undesired samples in a big this thing. This is one of the techniques, because you freeze the whole area and take the whole lump into the lab and then test that. So, that way you preserve the in situ structure. It has also been used to go for a lot of rehabilitation measures. You can see that somebody is assembling the frozen pieces here, freeze pieces here. Installation, of course, the figure is not very clear. Application of the freeze with electronically controlled refrigeration plant. Fast development around the pipes. The moment you cool material is inside, you white things form around the pipes. Is it not? Excavation following the completion of the freeze wall. Suppose the area is totally frozen, then you can start excavating, because it will not collapse. So, once after that you make the permanent wall constructed, and once that permanent thing is constructed, refrigeration can be shut down. That is it, as simple as that. It is a very temporary solution to some of the important issues. This is a very simple technology, but only thing is that people have not understood so much in many other developing countries how effectively one can do, but it has been a good practice in many places like West, and even in places like European countries, US and all that. The following figure shows an application in the Copenhagen metro project, where a pedestrian passage from a new metro station to an existing railway station was constructed on the ground. Here the question is that you are trying to have a new metro station and you would like to have a pedestrian passage, because people have to move from all the sides. Since the existing railway traffic had to continue, because you can't disturb the existing railway lines, the ground had to be frozen to avoid the risk of collapse due to excavation of the transfer tunnel. So, 200 kilowatt chillers, which are cooling systems, located on the surface, cooled the surface to minus 24 degrees, and then it was effective. Like this is how it was done. Pedestrian pathway between the existing, this is what they have created, and this is the shaft one, vertical cooling systems. These are vertical cooling systems, horizontal cooling systems. They have a metro tunnels here, like which are tunnels already working. These are all the systems. Then your trains are going, but then they are able to use a system like this, which is quite effective in solving that problem, which means that they have done a solid engineering job in locating all these things, and they have perfected the system of freezing technology here. Okay. So, now these two techniques are something very like what we discussed about thermal modification and all that are quite involved, and I would like to just discuss another ground improvement technique. The thing is that we have been there are many techniques that are there, like in the initial stages we talked about what we call the dynamic compaction, then even the blast inducing densification is also one technique, like similar to that. Normally this goes with that, but then since the coverage is in this form, I just want to complete this as well. And in the blast densification, it is again like as opposed to this, also again brings out the changes in the soil structure. Of course, it is more about removal of water only. It densifies relatively clean erosionless soils. It increases the density of the loose granular deposits above or below the water table. The technique is quite suitable to both. And what we do is that we try to create some explosives. You introduce blasts, like there is some 10 meters of area which is there, sand deposit. You put some place in some 10 meters down somewhere a blast, then trigger it, then the whole area settles. So, the consolidation is there in that soft soil area, in the not soft soil, sandy area. You are trying to accelerate the, the thing is you try to densify the whole area, that is the actual system here. You are essentially trying to densify. In this process what we do is that we try to temporarily liquefy the soil. We try to liquefy a soil a bit, and then what happens, there is a temporary development of pore pressures. This causes the particles to arrange to a higher relative density as excess pore pressures dissipate. You must have seen the case of a sand boil, in which the liquefaction occurs, then there is a settlement of the ground, and then the pore pressure comes out. So, once the pore pressure comes out, that area is slightly densified, and so the excess pore pressures will be dissipated. And we have done this sort of experiments in the lab, where there is a saturated soil mass, and with a loose density, if a bit of vibration is there, then there is a settlement, and then the water table is at the top. So, water, you can see that there is a water table. Initially the water table and the ground level are same, but then once you vibrate it, it goes down, the natural ground level goes down, and you have, say for example, 1 meter of sand, 1 meter of water lying, which means that there is 1 meter of settlement that occurred because of the vibration. So, this vibration, how to introduce this vibration? Can be introduced using some sort of blast, which can be, so blast induced densification is a very important system, and it has been used to treat soils up to depths of about 40 meters. As the depth increases, the size of the charge necessary to destroy the soil structure and liquefy the soil also increases. So, this is a very important concept. People have done lot of experimental work, analytical work on this. And how do you actually understand and calculate the system? As I just mentioned, the excess pore pressure and the settlement due to explosion are related to the ratio called NH, which is nothing but the weight of the explosives divided by the radius radial distance from the point of explosion in meters. So, this is what is called Hopkins number, and if you know the weight and the radius, you can get this number. Actually, studies have shown that if the NH is less and then in the range of 0.09 to 0.15, liquefaction does not occur, and the equation can be used to estimate the safe distance from explosion. Like the thing is, okay, you would like to densify some 10 meters or 15 meters of area. How do you get it? What is its radial distance? Say for example, if you put a blast at 10 meters level, how much of area could be really densified? So, is it all 10 meters could be densified? How do you do that? So, this can be understood from this point. Say for example, I will give a small example. You take NH as 0.12 and the weight of the explosives as 10 kgs, it can be 1 ton or whatever, radial distance from the point, if you use this expression, it could be 20 tons, about 17 point, if you use these numbers NH and all that numbers, you get R equal to 17.95. This number gives you the safe distance. Okay. So, based on this is a fixed, and the weight, how much of weight you can use. So, you can calculate what is a safe radial distance, which can be used, which is very useful in design of the blast induced vibration system compactions. So, for example, if you want 10 meters only, now in this case you can reduce the weight here, and then you can calculate what is that area to be compacted by this method. This is a very important point. So, you have some sort of expressions developed in Netherlands which relate the for example, the pore pressure increase as a function of in situ effective stress is given in this form, like say 1.65 plus 0.65 natural logarithm of NH. This is a similar type, where NH, as just said, we did, and W also we have a similar thing. So, the thing is that if you want to have a good densification ratio, okay, like the densification ratio, we would like to see that the for good compaction, it should be about 0.8, So, one can get this what should be the NH value also. So, if you are looking at the pore pressure ratio, what it means is that you are looking at a pore pressure ratio of 0.8 divided by the initial effective stress. So, one can really design this NH, and we also have in the previous equation some term related to the radius. You can combine some of these numbers and get some estimate, but the important thing is that now lot of analysis methods are available. One should use some of these empirical equations with caution. One can do a systematic study on this and then come out with actual guidelines. In fact, the best way would be to do a field case study, in which first thing you should do a trial test. Okay, I have done using a charger of 1 ton or say 500 kgs. What is the distance at which the area gets liquefied? You must be able to roughly calculate depending on the soil type, and then use that as a basis for refining your designs. There are some case studies here. One is a bridge location, and the soil in this case was a loose silty sand with gravel and boulders. Under the seismic event, the soils would be susceptible to liquefaction, which could result in the proposed bridge series being damaged or destroyed. Now, studies show that the soil has a tendency for liquefaction, and then it may give trouble, lot of difficulties to the proposed bridge. So, which means that the area should be compacted. In the field, of course, we have studied many methods of say for example, dynamic compaction. There are stone columns, there are so many techniques that we did, and underwater there are some methods and all that. So, in this case, sometimes if we are again looking for a very cost effective technique here, and if you can achieve the cost effective technique by any of these means, it is nice. So, you can use either, say for example, in a given situation what you call a dynamic compaction method, or you can use the densification by blasting. You can just do whichever is cheaper, and then go ahead with whichever is convenient and cheaper, right, because it needs a lot of equipment. There are many issues involved in both techniques. So, this Washington State Department of Transportation looked for several ground improvement techniques and found that the blasting was the most economical technique, and then they did some Becker penetration tests, showed a large increase in the liquefaction resistance of soils at this site. So, in fact, they did a lot of analysis also, and then cost analysis as well as the feasibility of doing the work in the site, and then when they could see that by blasting this has been effective, they went ahead with blasting. Then there is another technique, again another case study, in which blast densification was used to densify foundation soils for a large one-story manufacturing facility. Again, here the building has lot of alluvial deposits beneath in the foundation area, and it is saturated very loose to loose fine to medium fine grained sands with trace of silt and gravel. So, the soil which is very liquefiable is there. So, a seismic evaluation indicated the site would liquefy under the seismic event unless the alluvium was densified. If you do not densify the alluvium, the possibility is that you have liquefaction, and then it could really lead to damages to the manufacturing facility. That is the inference. So, the seismic analysis was done, and then they got some seismic coefficient or whatever design earthquake motion was arrived at, and then when they verified in the design, they found that could lead to what is called liquefaction. So, blast densification was selected over dynamic compaction, vibro compaction as the best alternative. As I just mentioned, this was found to be economical. So, a blast densification program was conducted at the site to verify the increase in soil density, determine the optimum blasting parameters, correlate density improvements with surface settlement, and to obtain ground vibration data. In fact, you have to do particularly when you do blasting, the problem is that, as I just mentioned, the propagation of waves, and it should not cause damage to the nearby buildings or nearby facilities, and blasting may be useful to you, but it should not lead to problems of the neighbors. So, one should really measure what are the vibrations, ground vibrations, like vibrations at the last point, vibrations to the depth, vibration in the lateral extent, and also correlate them with the surface settlements, density improvements, and parameters, like blasting parameters is nothing but the charge and the spacing and all that, whatever. Okay. So, they did cone penetration test, in this case electronic cone test was done before and after, and the results showed that the soil strength was subsequently it's improved, and it increased to resist the design earthquake at the site. What is required was that essentially they are looking for a very good ground improvement technique, which is required to match the design earthquake force. So, once you are able to achieve this, then they are also able to confirm this with many of these field observations of CPT tests, and they also had enough soil data to confirm that their design is correct, and finally they have been successful in conducting the blast densification program. And as I just mentioned, it has been quite cost effective compared to even the standard dynamic compaction methods and other methods of ground improvement. So, what I would like to highlight to you here is that what we discussed, I mean, in this particular things was that we are able to use thermal methods and blasting methods, and to improve the considerable, they need considerable expertise, it is not just simple, and you need to do some sort of trial test sections, and design and implementation is also quite involved. It is not easy to do this analysis, because standard it is not simple to do the analysis, because the methods of analysis themselves are very crude. Design is also not simple. Design could be easy, but at the same time to verify it is something that one needs to worry about it. So, what I just mentioned was that you should do some trials in the field, and then see if whatever design parameters you have taken are satisfactory or not. Then once you do a trial testing and then back calculate and check your design, then one can implement in the field, and also verify with many other like you can use lot of instrumentation to check if the technique worked in the field. Thank you.